If I see a problem involving one single force, what do I do? Well, it's kind of a trick question because it depends, right? It depends upon what that single force is. We know that we can always use the equation F is equal to m times a. F is equal to m times a stands for the net force. The net force is equal to the mass times the acceleration. And if there's only one force, whether it be friction or whether it be gravity or whether it be some other kind of force, if there's only one force, we can always describe it by that equation. Now, we can sometimes describe the one force by some other equation as well. Maybe F is equal to mu times the normal force if we're talking about kinetic friction. If we're talking about static friction, then the maximum force could be equal to mu times the normal force. If we're talking about some other force, maybe like gravity, we could say F is equal to m times g. G being the gravitational acceleration, 9.81 meters per second squared. But the bottom line is, when we're solving for one force, we can always use this, and we can sometimes use one of the other equations as well. If we're solving a problem involving more than one force, what do we got to do? 3 letters. Well, before that, that's 3 words, but you're close. Let's draw a free body diagram. In the end, we do have to, Ethan, add them up, you're right, but we're going to draw that free body diagram first, primarily to make sure we get the signs right when we go to add them up. So if it's a multi-force problem, more than one force is acting, you're still going to use F is equal to m times a most likely, but before we do that, before we add them up, we're going to have to make sure we draw a free body diagram. Free body diagram means what? Or sorry, FBD. I guess we just answered that question. FBD means free body diagram. What's another word that we can substitute free body diagram for? FBD. It's a way to help us remember. Yeah, force, right? It really stands for free body diagram, not force body diagram, but it's a way to help us to remember that a free body diagram shows all of the forces acting on something. Now, we can often put something else in there as well, although we don't need to. Sometimes if we have the mass of the object, then we're going to draw the mass of the object right onto the object. It's not necessary, but it's okay to do that as well. Look, we got to write down our given somehow, and if we've got a mass and an acceleration and an initial velocity and so on, we might as well just put it right on the free body diagram because we've got to write it down some way anyways. Now, once we've got the free body diagram drawn, then what are we going to do? Ethan, what are we going to do after we have the free body diagram drawn?
Add them up.
Add them up, good. And to add them up, we're going to say F net is equal to the sum of the forces. And maybe it's F1 plus F2 plus F3 plus whatever, or maybe it's FA plus FB, or maybe it's FC plus FF plus FQ. It doesn't matter what those forces are, we're going to add all of those forces up. That is, if they're all in one dimension. Okay, if we've got on 2 planes, 2 dimensions, X and Y, then all bets are off. We're going to be able to deal with that shortly, but not today. Okay, right now, we're dealing with problems with multiple forces in one dimension. All right, then what? Then what? Well, it could just be, if we're looking for the net force, sub any numbers and solve. If you're looking for the acceleration, then you're going to substitute F net with m times a. So that F is equal to m times a equation that I said is valid anytime you have anytime you have one force is also valid anytime you have more than one force. It stands for the net force, the total force, whether it be 1 or whether it be 15. Let's replace F net with m times a. But that's still going to be equal to the sum of all of those forces. Sum any numbers, solve. The reason we drew a free body diagram again was to make sure that we get the signs correct. So if you have it drawn to the left or down, then make sure your force is a negative value. If you have it drawn up or to the right, then make sure your force is a positive value. Does that make sense? All right. We had a couple questions for homework on page 132. Let's take a look at those questions right now. Let's have a look at another example. Now 3.6 on page 150 says 2 athletes on a team A and B are practicing to compete in a canoe race. Athlete A has a mass of 70 kilograms. Athlete B has a mass of 75 kilograms. And the canoe is a mass of 20 kilograms. A can exert a force of 400 newtons forward, B is 420 forward, and during the paddle, the magnitude of the water resistance on the canoe, this would be the equivalent of air resistance or friction, except we're going through the water here, is 380 newtons. What's the acceleration of the canoe here? So let's draw a free body diagram. Clearly, there's multiple forces acting. Listen, we know that F is equal to m times a is valid, because it's valid whenever you have a single force or multiple forces acting. But if we have multiple forces, then we got to do a little bit more than just F is equal to m times a, starting with a free body diagram. So let's draw that free body diagram. I want to simplify this a little bit. Here's my canoe and my two guys, or my two people in the canoe. What's the mass of that canoe slash person A slash person B? What mass do I use there? If I'm just going to label this and try to simplify it, do I use the 70, the 75, the 20, or some other value of mass? Yep, wait. It's all of them. In the end, look, person A is on the canoe, so is person B. The canoe is part of this pair of people. The people are one with the canoe. It's like you're propelling, it's not like you're propelling a person forward and then another person forward and then a canoe forward. The people are on the canoe. It's like one object. As far as physics is concerned, it's one object, right? Nature doesn't know that it's trying to push three things together. Look, if I was trying to push you across the room, would I account for the mass of you and the mass of your glasses and the mass of your shoes and the mass of your clothing all separately? Of course not, right? Of course we'd include it all as one. This is no different. The mass of these people and whatever they're wearing and their canoe is all together. It's all one object. So we're going to draw it as one object, and we're going to say the mass of that one object is 165 kilograms. 70 plus 75 plus 20 kilograms. Now remember, that mass technically isn't required to be labeled on my free body diagram, but I might as well, because I'm going to have to write it down somewhere, so I might as well just put it on my free body diagram. Now, what do we got for forces acting here? It says athlete A can exert an average force of 400 newtons forward. So let's draw that. Let's draw that this way. Let's call that FA. And we'll label it as 400 newtons. This is important to label on your free body diagram. And the mass wasn't critical. The forces are, because that's what a free body diagram is. We got another force, person B applying a force of 420. Tell me when to stop drawing force B. Tell me when to stop.
Stop.
Somewhere around there, right? It's going to be a little bit bigger. Not much, but a little bit bigger here. We'll call that FB. 420 newtons, a little bit bigger because it's 20 newtons more, so 5% more. Now we also have a force of, usually at this point it's friction or air resistance. In this case it's water resistance. You know that if you swim through the water, there's a lot of water resistance, right? Or try to run in water, the amount of water resistance that you encounter. Which way is that going to act, the 380 Newton force? Left, right, up, down? It's going to act to the left, right? And how do you know it's to the left? Yeah. In the absence of water resistance, which way are we going to move? Like, let's say there is no resistance. Which way do we move? To the right. And if we move to the right and there is water resistance, then that resistance is going to act to the left, opposite to the way that I move. We're going to draw that a little bit shorter than FA. We're going to call that, I'll call it FR for the force of resistance. You want to call it FW for the force of water, or FX, or whatever you want, F1, whatever you want, doesn't really matter. Okay, you're not getting marked on what you call the forces. Whatever makes sense to you is what you should call it. Okay, that's 380 newtons. Do we have any more forces acting on this 165 kilogram mass of canoe slash person A slash person B? Do we have any other forces? Yeah, we have gravity and the normal force. Why am I not terribly concerned about gravity and the normal force here, Ethan? Yeah. Whoops. What have I done wrong here? Yeah. Just made a little mistake there. The normal force is acting upwards. It doesn't matter where I draw it, but I have to draw it the same length as gravity, and I have to draw it in the right direction. Now let's cross off gravity and the normal force. Listen, if this canoe isn't being, it's not on some kind of angle, which would be difficult actually for a canoe to be on some kind of angle when you're talking about water. Water has this amazing ability to go flat, okay? But if it's on a flat surface and it's not being pushed up by something else like, like a, I don't know, a helicopter with a rope or something like that, then the normal force will be equal to gravity every time. All right. Remember we said we draw a free-body diagram, cross off things or cancel out things that cancel. We've done that. Now what? Now what? Who's next? Let's say, Jack. What do we do next?
You gotta write down the equation.
Yeah, what equation do I write down?
Isn't it like F net
Yep.
equals FR plus F?
Yep. F net is equal to the sum of the forces. Fr plus Fb plus Fa. Now, some people might not like what I just did here. Some people might be a little more organized than that and like to put them in alphabetical order or something like that. Fa plus Fb plus Fr. Is that okay? Would that be okay if you did that? Yeah, of course. Like if you add 1 plus 2, it equals 3. If you add 2 plus 1, it equals 3. It doesn't matter what order you add them in as long as you include all the numbers, right? So let's say F net is equal to Fr plus Fb plus Fa. Now we're looking for the acceleration, so there is one more step that I have to do here. Leah, F net is also equal to what? Good. F net is also equal to mass times acceleration. So ma is equal to Fr plus Fb plus Fa. Okay, write these steps down. Even if you think you can skip them, write them down. Okay, it's amazing how sometimes just structure in solving a problem is helpful. Not like it's helpful to me when I'm marking it, but it's also helpful to you when you're solving these problems sometimes. So write these steps down. Now, what do I put in there for mass? 70, 75, or 20? Or 165? Jake, what do you think I'm going to put in there? 165. It's the whole thing that's being accelerated, right? It's not just one guy or one girl or a canoe. It's the whole thing. We don't know what the acceleration is. What's Fr? Erica, what's Fr, the force of resistance, the water resistance? Close. I'm going to write that down, but you're not quite right. It's not 380. It's not positive 380. It's negative 380. And it's negative because it's going to the... Good. Good. Fb, is that going to be positive or negative? Ryan, is that going to be positive or negative, that 420? Yeah, it's positive because it's going to the right. And of course, the other one, 400 is going to be positive as well. So we add up the right-hand side, simplify this a little bit. 420 plus 400 is 820. Subtract 380 would be 440. Is that right? So we're going to say 440 newtons on the right side, 165 times A, and A will be equal to 440 divided by 165. That gives me 2.67. 2.66667 meters per second squared. How many digits should we be in here? How many digits is this? 2. How many is that? 2, 2, 3, 3, 3. Final answer should be? Yeah, we got to look at all the numbers that we used, and we used those 2-digit numbers, so my final answer will be 2 digits. Okay? You guys feel okay about that? Like that's pretty much those 2 questions that we were talking about earlier that we said were homework, except that in this question, we had to add that extra step and include m times a in there, as opposed to just saying F net is equal to the sum of forces. Okay, we did everything that we did yesterday, but now we're adding m times a in there as well to find the acceleration. All right, All right, let's have a look at these two questions, please, on page 150. Or sorry, this one question on page 150. All right, men's four-man bobsled event, we have a maximum mass of 630 kilograms. It doesn't say that that's what we're actually using. It says that's what we're allowed to use in competition. During a practice run, we got two riders exerting forces on this bobsled. Here's the bobsled. It doesn't matter what the shape of it is. Okay, there's my non-aerodynamic bobsled. We've got a mass of this bobsled of, it's not 630 kilograms. That's what we're allowed to have, but we don't have that. Okay, in this case, inside the bobsled, or the bobsled and the passengers inside the bobsled are simply the 255, the 98, and the 97. 98 and 97 give me, what is that, 195? 195 plus 255 is 450. So the mass of my bobsled here, 450 kilograms. I don't care that I'm allowed to have another 180 kilograms here. That's irrelevant. Okay, what's important is what's in this bobsled now. Now, are there two more people? Are these two riders that are pushing the bobsled? Absolutely. Do we care about what their mass is? No. We only care about the mass of what's being pushed. We don't care how heavy the thing is doing the pushing. Okay? If I'm pulling on you with a force of 50 newtons, or some big, massive football player is pulling on you with a force of 50 newtons, does that matter to you? It's 50 newtons that we care about, right? Not how heavy the person is doing the pulling. So, how heavy are these two riders that are pulling with these forces? I don't care. All I know is that one rider is pushing with a force, we'll call it F1 of 1,200 newtons forward. Actually, call it FA because they already named them A and B. 1,200 newtons forward, and the other is, sorry, that would be FA is 1220, isn't it? So we're going to say FA is 1220 newtons forward, and we're going to say FB is 1,200 newtons forward. What do we got? We got a force of friction here. This 1,300 meter course is really irrelevant, right? We have a force of friction. Which way is it going to act? Caitlin, which way is friction going to act here if both of these guys are pushing it to the right? Yeah, it's going to act backwards, and it's a lot less than these, so I'm going to draw it somewhere like this. FF is equal to 430 newtons. Now we have two more forces acting here that don't really matter too much, but I'm going to draw them anyways. What are they? Tina, what else am I going to draw in here? Yep. Normal force, which is acting up, right? And gravitational force, which is the same value, which is acting down. Same value, and that's why we can cross them off, right? And that's why they weren't that important. All right. As I was walking around, checking to see what you guys are doing, I saw some people drawing the applied force, FA and FB, in the opposite direction to the left, and the force of friction to the right. Is that okay? Sure it is. It doesn't actually say that this sled is being pushed to the right. It could absolutely be pushed to the left. But if it's being pushed to the left, then friction would have to be to the right? We just have to make sure that friction opposes the motion, whatever that is. Now, be careful, because sometimes it'll actually say it's being pushed to the right. But if it doesn't say, then you choose the direction. Yep?
So forward can just be any direction?
Yeah, absolutely, absolutely. Forward can be any direction. Like if I'm sledding down a hill, you would say that would be forward down the hill, right? Like the fact that it's down and to the left, who cares? It's forward down the hill. So, like when I read this question, like to my mind, like this just pops out in my mind right away that this is forward, but it depends upon how we're defining forward. And a thing like this, it could absolutely be a different way. All right, what's next? Ben, what's next? Yeah, what's the equation? In this case, at least, what's the equation? Okay, she said FA, Ben's saying FA plus FB plus, yeah. Why are we not including FG and FN? Yeah, because they cancel each other out, right? They balance each other. The net force there is 0. If it wasn't 0, then we would have an acceleration upward or downward as well. Yeah, but right now we don't. Okay, so he said FA plus FB plus FF. I probably would have said FF plus FA plus FB because that's the order they appear. Does it make any difference? No, whatever works for you, right? As long as you include them all. What's next? McKenna, what's next here after I say F net is equal to FA plus FB plus FF? Good. Now, if I'm just looking for the net force, I'm going to leave it as is, right? But if I'm looking for the acceleration, like in this case, then I'm going to switch it to m times a is equal to FA plus FB plus FF. And I'm going to sub in some numbers. FM is 450 kilograms times A. FA will be, FA, Alexis, is going to be what? 1,220. Is it positive or negative? Yeah, with the way that I have it drawn, it would be positive. If you had it drawn it to the left, you probably would have made it negative, right? FB is going to be positive 1,200. And FF is going to be a value of what, Maddie? Good. If we drew it to the left, right, then we're going to make that negative 430 newtons. So let's add these up. 1,220 plus 1,200 is 2,220 minus 430 would be 1,820, 1,790, I think, on the right-hand side. Equals 450 times the acceleration. Now, how do I find A? This should be easy now. 1,790 divided by 450. Did I make a mistake there? 1,220. I think I might have made a mistake with my adding here. Yeah, 1990, not 1790. 1990 divided by 450 is 4 I got 4.42222. How many digits should we be in here? Let's go back to my original data. Not this one. Why do I not care about this one? Because I didn't use it, right? I care about this one, which is 4 digits, this one, which is 4, this one, which is 3, and 2 digits, yeah? So final answer should be 2 digits. A is 4.4 meters per second squared. As I was walking around, it looked like most people got that. Is that right? Yeah? Good. 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 All right, I'm going to give you a few minutes here right now to work on some questions in your book. Not enough time to finish them probably, but a few minutes here. I want you to do questions 1 to 4 and 8 on page 136. 1 to 4 and 8 on 136. Now, I'm going to ask you, as you're doing these 1 to 4 and 8, I'm going to ask you to skip question B in number 2 because that's dealing with some angles. We'll deal with that later on this week, but not for now. Okay, so 1 to 2A, and then 3, 4, and 8.